Problems in 2 dimensions start getting a little bit trickier when we shoot something off at an angle. And so I'm going to call this type of a problem a type 2 problem because it's harder than a type 1, but it's not as hard as a type 3. Okay, so this is a type 2. So I shoot something off at some initial velocity at some angle, and it goes and then it lands. This is sort of like me tossing a baseball to somebody. It goes in sort of this parabolic arch. The first thing, and this is where the summer work comes in, the first thing that we need to do is start thinking about this velocity, not in terms of the total direction. The total velocity is at an angle, but remember, we are splitting everything into x and y. And so we need to take this velocity and split it up into the little velocity that's in the x direction, or v naught x, and the little velocity that's in the y direction, or v naught y. Okay, so remember these are sine, cosine, tangent, SOHCAHTOA. So the sine of theta is the opposite, v naught y, over the hypotenuse, v naught. And so the initial velocity in the y direction is simply v naught sine theta. And then we take the cosine of theta is our adjacent, or our v naught x, over our hypotenuse v naught. And we'll move this to the other side. So our initial velocity in the x direction is v naught cosine theta. These are typically what you'll find. There might be once in a while that you're given a weird angle. Like if, I don't know, if you shoot it, you might be given a weird angle. So I wouldn't memorize this per se, but if you did memorize these two things, just remember it is for this angle and not like, not for this angle up here, because you would get different values. Okay, so then we start thinking about, okay, well, let's just talk about our y direction. In the y direction, our initial velocity in the y direction, our final velocity in the y direction, our maximum height, or y final, our original height, y initial, acceleration, and remember time is the thing that links us, so I'm just going to put that over here. Okay, the easiest piece is acceleration in the y direction. That's just opposite of g, right? Or -10. Initial velocity in the y direction, we found it here, v naught sine theta. Final velocity in the y direction, this depends on what you're trying to find. And so before you start talking about what is the final position, you need to start talking about like what the problem actually wants. So if the problem is asking like how high does it go, well, then we want the position up here, right? We want the final position to be the total height. But if it's asking like what's the total distance that it travels, well, you might want the final position to be over here. So this final velocity in the y direction, if you're talking about the top, well, just like if you throw a ball up in the air, that y velocity will become 0, and then it will travel back downwards. If you're talking about the velocity being down here, or the final position being down here, well, this will just be the opposite of the initial velocity. Regardless, an initial position in the y direction is 0 meters, right? Because it starts here. Okay. So let's just talk about what happens if I want to find the total. No, let's do the whole thing. So velocity final is going to be negative v naught y. And our final position is going to be the height. So our x position then, the stuff that we know about the x, well, we know our initial velocity in the x direction is v naught cosine theta. That is going to be our total velocity because our acceleration in the x direction is 0, right? And so the time matters, and then maybe we could find our change in position in the x direction, or the range. to be our final minus the initial position. Where the initial position is going to be 0. Okay, I'm going to pause here. I'm going to check some notes, and then I'm going to come back. So if you wanted to find like the time that it's in the air, right, you could use this equation. Velocity final is the velocity initial plus the acceleration times the time. This is a good equation to use with the y direction, because we know that the final velocity and the initial velocity, even if we're talking about the y direction, are going to be the same. This is the opposite of v naught y, the initial velocity in the y direction. This is v naught y, initial velocity, plus opposite of g times the time. And so we move this to the other side, so we get 2. Velocity and initial velocity in the y direction is g times time, here and here. So our total time in the air is going to be 2 times the initial velocity in the y direction over g. This means that the half the time in the air, the time it takes to get to the top here, is going to be half of this time. So if total TOF means time of flight, is 2 v naught y over g, then t 1/2 is just v naught y over g. At this point, it's pretty easy to find the height at which the highest point that the ball reaches. So we can use our change in position is our initial velocity times time plus 1/2 acceleration times time squared, right? So if I was looking for the height here, there are a couple things that I could do. I could think of this, and I like to think of it as a first half problem or a second half problem. So I could think, oh, I'm shooting this off at some initial velocity and it's traveling upwards and it's reaching some height. And so I have an initial velocity in the y direction that I have to deal with, and then it travels up, that velocity becomes 0, and that's where I'm going to have my maximum height. You can do that. But if you have an initial velocity, then you have to deal with it in this problem here using my favorite equation. So if instead of you thinking of it as a first half problem, think of it as a second half problem. So I just want to think about what's happening during the second half, and then it becomes a whole lot easier. So if I think of this as a second half problem, then this is my initial position. Oops. This is my initial position up here, and this is my final position down here. Which means if my initial position is up top, then my initial velocity in the y direction, if I make all of these y's, the initial velocity in the y direction is 0. This looks exactly like finding the time if the ball is dropped. So if I'm solving for the height, then the height is just 1/2 gt squared. Remember, because this would be negative h and negative g, and they'll cancel. So I can just take this here and plug it in for my time right here. So the height is going to be 1/2 g times 2 v naught y over g squared. So there's some math here, right? So we get 1/2 g 4 v naught y squared over g squared. This squared will cancel with this squared. 4 divided by 2 is 2. So our height, the maximum height that the ball is going to reach, is going to be 2 v naught y squared over g. And if we plug in this, this for our v naught y, then the height is again, you don't have to memorize this. Physics, AP Physics is very little like plugging numbers in, but good things to know, all good things to know. So if we keep going with this, the next thing that we'll want to calculate is going to be the range, or let's highlight a different piece. The next thing we want to know is what the range is. So the initial position in the x direction to the final position in the x direction. And remember that range doesn't ever really change. The range, right, velocity is the change in position over the change in time. So the range is going to be the velocity times the time. And this is the velocity in the x direction. And so this range is actually, we just substitute in the things that we know. So the range is going to be equal to v naught x times the time, where the velocity in the initial velocity in the x direction is v naught cosine theta. And we can do some funky things here, but we have the time. Let's use this time given here. The time that the ball is in the air is going to be 2 v naught y over g. And remember, v naught y is v naught sine theta. So I'm just going to put that in. V naught sine theta over g. I have 2 v naughts, so that's going to be a v naught squared over g. And this cosine theta, sine theta, that's like a trig identity function. You can look it up. I believe cosine theta, sine theta becomes the sine of 2 theta. If you memorize any equation at all, this is the one to memorize, the range equation. The range of a projectile that is launched and lands from the same position, so same height, is the initial velocity squared times the sine of 2 theta, where theta is the angle with the ground, over g. V naught is the total initial velocity. Boom. This is a fabulous equation to remember. Okay, I think that's it.